Good morning. My name is Scott Auerbach. I'm from the chemistry department at UMass Amherst, and I'm absolutely delighted to launch our session today, trying to figure out how to use a cycle of carbon to have a carbon neutral source of energy at scale. That's what we're about here today. So I'm absolutely delighted to start by introducing our keynote speaker of the morning, Professor Lee Lynd, who's the Paul and Joan Queneau Distinguished Professor of Engineering and Adjunct Professor of Biology at Dartmouth College. And he will be talking about the decarbonization using cellulosic biofuels.
Thank you, Scott.
Yes.
So pleasure to, oh my, I haven't done anything, but thank you. Good to see you all. I think we'll have a great session, and I welcome you all. So let's get going. You've heard the title. So cellulosic biofuels, which I summarize as fuels from plants you can't eat, their blessing and their curse is that they're connected to everything. So a critic looks at that and says, ooh, that's a lot of things to get right and many things that could go wrong. An advocate or optimist looks at that and says, wow, think of all the benefits I can get beyond energy supply. And indeed, the connectiveness of cellulosic biofuels and bioenergy is generally greater than other renewable energy sources. And that means that, you know, in the PV session, they don't spend a lot of time talking about whether this is worthwhile. They just go get on with how you do it. And yet, as I think about a general audience like this, there's a lot of questions of could, should, and how related to land, climate stabilization, production technology, and ultimately people, which those four columns are actually my outline. So I'd like to acknowledge a lot of people on these different subjects. I'll only mention the underlined ones, which are lead authors of some of the papers I'm summarizing. In the land area, Andrew Ali and Leonardo Montero. In the climate stabilization area, a group led by John Field. Lignocellulosic conversion, Dan Olson and Evert Hulverda are group leaders in my group at Dartmouth. Techno-Economic Analysis, Xiaoyu Liang and Mark Lacer. John, if you check the fine print, you're in that list. Economic Development, Horta Nogueira from Unicamp in Brazil. The folks at Enchi Corporation, and acknowledge the support from the sponsors you see there. So first, land. Land is really important for climate stabilization. I go to lots of climate stabilization meetings, and everyone's talking about energy, which is fantastically important. I'm not up here to say it isn't. But check this out. If you haven't seen the global calculator, just put global calculator into Google. It's really easy to find. And so for all of these variables, each one of which has subvariables, they evaluate minimal abatement, ambitious, very ambitious, and extremely ambitious. I'm going to focus on three of them. One of them is diet, which is defined as written here. One of them is renewable energy, defined as written in the little bubble. And one of them is land use, and they are defined to be mutually exclusive. Ask yourself for a minute, which of these would have the largest climate impact? And the answer is diet the biggest, land use the second, renewable energy third. And so, frankly, you could develop your scenarios a bit differently, and you might get quantitatively different answers. But qualitatively, this is essentially the climate impact of land use and dietary choices is comparable to, individually by the way, is comparable to the impact of renewable energy choices, and we have to manage land wisely to stabilize climate with or without biofuels. This is a cumulative food supply curve, and so the way you read this is if you imagine a given number of hectares ranked from the least productive to the highest productive, then you would go to this curve and read over on the left, and that is the fraction of food that would be produced from all of this land. That's just to introduce it notionally. Here's what it actually looks like. So there's about almost 3 billion hectares that have a negligible contribution to food supply, less than 3% of dietary protein, less than 1% of dietary calories. And in that land is quite a bit, according to the FAO, quite a bit of potentially good agricultural land, which is an awful lot larger than the amount that is projected to be needed for additional food, although these subjects are controversial, but that's the FAO's view. This is a study that is under review right now, and it looks at the potential for intensifying grazed-only pasture land. People focus on cropland, but there's twice as much pasture land in the world as there is cropland, and again, it makes a negligible contribution to food supply at a global level, although I hasten to say a critical contribution to local livelihoods and impacting ecosystem services. But the point here is the intensification potential for variously constrained situations, all pasture, length of growing period 7 months, and pasture suitability index medium or better. I think the only point I want to make now is that the big hitter for all of these is sub-Saharan Africa. And so if we're talking about, that's where the land is, that's also where some of the greatest human development needs are, which I will close with. A little bit about climate stabilization. So according to the IEA, their modeling indicates that modern bioenergy is an essential component of the future low-carbon global energy system if climate change commitments are to be met. They single out the transport sector. They say biofuel consumption must triple by 2030, with 2/3 of that coming from advanced biofuels. That means scaling up current advanced biofuels by at least 50 times to keep pace with the 2-degree requirements for 2030. We are not on track to do that. They conclude that acceleration is urgently needed to ramp up the contribution of bioenergy across all sectors, notably in the transport sector. And by 2050, they're talking about 30 exajoules in a 75 exajoule transport scenario. So here's another indication of this. This was led by Lou Fulton, the lead transportation analyst for the International Energy Agency, looking according to the IEA 2-degree scenario, all the way out to 2075 about where transportation energy supply is going to come from. And about half of it is from biofuels, about 4 gigatons of carbon, and about 40 exajoules of energy supply. This diamond here is the total emissions compatible with the 2-degree scenario across the global economy. And so you see that if we don't decarbonize this, we have no hope of reaching the 2-degree scenario. And so 4 gigatons of CO2 is an awful lot to leave on the table. And key here is that about half of anticipated transport demand is amenable to decarbonization with batteries and hydrogen, and about half is not. Specifically, the aviation sector, battery-powered jets are very hard to imagine, long-haul trucking, and ocean shipping. So here is Shell's net zero scenario. It's striking that the primary energy from biomass in this scenario is equal to coal, oil, and gas combined, and also that bioenergy is the leading opportunity for negative emissions via carbon capture and storage. So to meet climate objectives, biofuels must be produced sustainably at lower costs than once anticipated and at levels much higher than current, likely requiring cellulosic, often called second generation or 2G feedstocks. How much land would that require? Well, it depends a lot what you grow and where you grow it. But here we have, for energy cane, which is among the most productive terrestrial plants, sugar cane, including both the sugar and the bagasse, sugar cane with just cane juice, all the way over to unmanaged grass and forest, exajoules on this axis. Keep in mind, if we're looking for 50 exajoules, we can be as little as 50 million hectares, depending on what you're growing. By the way, the eco-ecological zoning for Brazil says that there's about 65 million hectares in Brazil after you exclude all the forest, food production, et cetera, et cetera. So that would say that one country has enough land to have a shot at producing the global need for difficult to electrify or to provide by hydrogen transport. This is from the IPCC report, so here's 50 exajoules from a lot of different sources of biomass and bioenergy, and you can see that the high agreement, if you add these up, is well north of 50 exajoules. And so this is a figure that was published a long time ago, and this is the potential, and it's real potential, but as you appreciate, realizing a zero-carbon situation with plant biomass and biofuels is complicated, but we do need to remind ourselves that the fundamental cycle starts with removing CO2 from the atmosphere and the circular economy that Scott was talking about. Here is a more complete accounting, which is a little hard to see, but the equation, I think, will make some sense. The net mitigation is the emissions avoided from the fossil fuels you don't burn, minus the emissions of the biofuel supply chain, but you have to look at the change in above-ground carbon and the change in below-ground carbon, and then you may also implement carbon capture and storage. And you also have to think of the temporal dimensions, as is quite prominently featured in the literature. And so these are, when talking about the climate change mitigation logic, if you will, of biofuels, there are some very strong statements in the literature to the view that that logic is fundamentally flawed. I think that's wrong. This is my, and I'll give you my rebuttals in a moment, but this is my best summary my best effort to summarize the arguments that are made. So number one is indirect land use change, or sometimes called these days induced land use change. The basic idea is that displacement of food crop production on agricultural lands leads to induced land use change elsewhere, and that results in greenhouse gas emissions. The classical case being, if I take an acre of Iowa corn land, somebody's going to clear some forest somewhere, and that's going to release a lot of CO2. There's a grain of truth to all of these, folks. It's not that they're totally illogical. The carbon debt is a second criticism, and the idea is that forest harvest for bioenergy results in a large initial carbon debt that must be repaid before net climate benefits are realized. And the third one is the opportunity cost argument, that the restoration of native vegetation has equal or greater mitigation potential than bioenergy deployment. So just let the land do what it does. So here are the counter-arguments that I would offer. One, and I'll show you this data in a minute, current ILUC emissions for cellulosic biofuels are in fact about zero. So there's I mean, if something has and that's, by the way, without an intent to achieve climate benefits. If you actually manage land to achieve climate benefits, you could do much better than that. As far as the carbon debt, well, number one, if you use pasture or cropland, which does not start with a large above-ground carbon inventory, there's no issue with the carbon debt argument. And it is possible using forests, although frankly somewhat tricky, as long as you manage the forest to keep a constant inventory of carbon, then you can produce energy and displace fossil fuels. The final one is the one we go into in most detail in the paper John Field is leading. We look at the mitigation potential of cellulosic biofuels compared to native vegetation restoration. And this depends on the technology, either current or future. And keep in mind, if what you're talking about is greenhouse gas emissions per hectare, that's influenced by the tons of biomass per hectare and the emissions per ton. And they actually, as those two things improve, they multiply. So we have to be careful, are we talking about today's technology or future technology? With current technology, if you start with forest compared to leaving the forest alone, you get roughly similar climate benefits. But if you start with grassland or cropland, and I've there's a lot of there's a lot of pasture out there that's not cropland, you get much greater benefits with bioenergy. And with future technology, you get much greater benefits than forest or grassland. So we have a paper coming out, we have a paper about to submit that makes these arguments, but I'm giving you a preview. And here's the actual data, by the way, of a whole bunch of different models for the induced land use change, with zero being here. I've itemized the soil carbon change and the net effect, but look at the diamonds. They pretty well cluster around zero for both switchgrass and miscanthus. And again, this assumes that land use decisions are made without regard to greenhouse gas emissions. You know, when people talk about bioenergy with carbon capture and storage, so-called BECCS, the focus is usually on electricity. I think that, on the other hand, it's widely understood that biomass electricity is not particularly competitive. On the other hand, though, I think people have overlooked the potential of transport applications for carbon capture and storage. I think the argument is going, well, wait a minute, if I'm making a transport fuel, emissions out the tailpipe of a mobile device are uncapturable. I couldn't agree more. However, what's not realized is what biofuel technology does is to concentrate the energy on fewer carbons. And that means in the course of those conversion processes that a lot of the CO2 is actually emitted in a stationary way. And so, first of all, these are rather efficient processes. The projected thermodynamic efficiency is about 71% of electricity and fuel as a function of the biomass high heating value. But if you look at the base case, the sort of a current technology, this is one that maximized liquid fuel production. This is another future scenario from the literature. We're talking about at least 50% of the carbon being emitted in a stationary way. Moreover, a good fraction of that is from fermentation, which is essentially pure CO2. And the largest cost for carbon capture and sequestration is, in general, the capture, not the storage. And so this is actually, in my opinion, it's the lowest cost, scalable energy supply related carbon capture and storage opportunity. People talk about looking for gigaton scale negative emissions. Well, if we had 65 exajoules of biomass going to biofuels, and we used a middling number of 60% of the recoverable carbon per gigaton of carbon, that's a gigaton of negative emissions through biofuels, all right, just based on the stationary emissions. Well, okay, so again, that's a much longer introduction than one would need if we were talking about many other renewable energy technologies, but my experience is if you plunge right into how you're going to do it technically and you don't touch on those, people go, yeah, what about? And this is like one of the things that holds bioenergy back. So let's look at, and I will be talking specifically about biological processing. There is also thermochemical processing of biomass, which will be several of the talks this morning focus on. So within the context of biological processing, the field has been following a thermochemical pretreatment fungal cellulase paradigm. And as many of you know, this got started in World War II because canvas wasn't lasting very well. And so people began looking at that and saying, what's going on? It turned out that aerobic fungi were responsible. And at about 1980, this paradigm was established. Various things happened which you may recognize. In roughly 2016, there were 5 pioneer, I call them pioneer cellulosic ethanol plants built around the world, all based on this concept that involves thermochemical pretreatment, added fungal cellulase, adding a catalyst as a non-recoverable reagent, or at least very difficult to recover. Okay, so that's how we've been trying to do business. Here's some data from a recent review that I wrote with others, I should mention. You're familiar with many of these projects, over half of which have been sold or abandoned, by the way, so this is not a success story. This particular, the field failed to launch based on this technology. So these are all based on that paradigm. They're all based on a grass feedstock. 4 of the 5 are based on yeast, and they're all expensive. The annualized cost of capital is greater than the selling price of ethanol, even if oil's $100 a barrel. These are quite expensive still, and they've proved to be more expensive than people hoped they would be. Well, why is that so? Is it because of the cost of the feedstock? No, actually. Cellulosic biomass is less, the purchase cost of cellulosic biomass on a $ per gigajoule basis is less than that of petroleum. It corresponds to, even at $100 a dry ton, it corresponds to about $39 a barrel, all right? Is it ethanol that's the problem? No, this is likely the cheapest biologically derived fuel for the indefinite future. The first-of-a-kind plants have to learn by doing. That is a definite contributor, but the most important reason is recalcitrance. Nature has evolved cellulosic biomass to be difficult to attack and difficult to take apart. From a process point of view, it's the process steps that are specific to solubilizing cellulosic biomass so that you can make it amenable to the wonders of biotechnology. As long as it's an insoluble particle, it's outside the cell. It has to become soluble, and it's the steps associated with solubilization, the fungal cellulase and the thermochemical pretreatment, that are responsible for this being expensive. Biofuel deployment has been largely stagnant over the last decade for at least 2 big reasons. One is there were really high expectations in the bonkers for biofuels period. The economic viability was not met. But also, and don't underestimate this, divergent assessments on whether and how these are beneficial. You know, if we want the next decade to be more successful than the last one, and according to the IEA, that's a critical need for biofuels, we need to think about doing things differently, and I don't see that trend in the field yet. I think I see us sort of saying, well, we're just going to keep, grinding the same wheels we've been grinding. So I call it a 2G 2.0. It would be very good to resolve divergent assessments. And it's urgent because the climate clock is ticking. Look at how much better these other renewable energy sources, bless them, we need them. This is not like only one solution city, all right? But wind was predicted 10 years ago to provide 17.8 gigawatts of generating capacity in the US. It actually provided 90. PV was predicted to be 0.17. It exceeded that by over 100-fold. Cellulosic biofuels actually fell short of the target by 3 orders of magnitude. This is a log plot. According to the Renewable Fuel Standard, investment in 2016 was 2006 was roughly equal for biofuels, wind, and solar. Well, since then, biofuels has faded away to almost nothing, and as you know, wind and solar have gone crazy. This is not what success looks like, all right? We really need to approach this differently. And so think about it this way, especially batteries. Batteries have changed chemistry 4 times, and they went from space application, where cost didn't matter, to consumer electronics, to automotive, to grid storage. Kind of this 2-dimensional space navigated it really well. Similar story with solar electricity. But for cellulosic biofuels, a decade ago, entrepreneurs, investors, and the government proceeded on the premise that big things could be done fast with the technology in hand. Consistent with this premise, the field generally looked beyond stepwise deployment, saw little need for alternative technological paradigms, and invested in large greenfield plants. But in light of the industry's failure to launch, combined with continued demonstration of need, it's appropriate to look for other paradigms. Well, you know, a really basic question that could have been asked a long time ago and largely was not is, what are nature's best biocatalysts at taking apart lignocellulose? We're going to assume for the moment we're going to do this biologically. It's actually rather interesting to think about why this question wasn't answered. I'm a bit of a student of this history, but we don't have time. So this is not a question that you answer in just one figure, but I'm going to give you some indication. We could spend the whole presentation on this topic. But let me just point out, so here's a bunch of different biocatalysts, all on the same feedstock with some controls. And I'll just point out that here is a thermophilic anaerobic microorganism, Clostridium thermocellum, that's in this test under these conditions about twice as effective as industry standard cellulase. And we've done 5 different feedstocks, 10-fold range of catalyst loadings, 10-fold range of substrate loadings. I'll let you read all of that, confirmed by multiple labs. The green is Clostridium thermocellum for a whole bunch of feedstocks, including genetically modified feedstocks. The sort of brown color there is Trichoderma ricei. And so you can see that in all of these feedstocks and a broad range of conditions, not all of which are shown here, nature offers better catalysts than the ones we've used to launch this industry. Simple as that. And the more you can do with biology and the less you have to do with essentially process engineering, beating the substrate up, the better. On the other hand, we'd really like to get high solubilization of the lignocellulosic feedstocks here, the poplar, the cornstover, the switchgrass. And the best nature can do is maybe on those, cornstover is a pretty reactive one, but nature needs some help. So how are we going to augment nature's ability? Well, the biofuels field's answer for the last 35 years has been thermochemical pretreatment. Let's add heat and chemicals and make the stuff reactive. Nature's answer, though, looks like this. So my son's a dairy farmer, and I took this picture of the cow. Notice that I apologize because they know the names of all the cows, and I don't remember the name of this one. I should ask. But notice the cow's not doing this, which is what it would do to cut biomass. It's doing this. It's grinding it. And actually, rumination, which is this process of the grass going back and forth between the rumen and being chewed, it increases the surface area up to 10,000-fold. Moreover, if you look at yeast, yeast is really, really resistant to chemical inhibition, but not very resistant to mechanical insult. These nature's best cellulolytic microorganisms, though it's the reverse. They're not particularly resistant to chemical inhibition, which arises from pretreatment, but they're very resistant to mechanical inhibition. Just a little anecdote. A few years ago, when I was getting my master's in bacteriology, we used to make cell extracts where we would expose cells to 10,000 psi and put them across a little orifice. And if you got 10 or 20% breakage on these gram-positive microbes, you were doing really, really well. So these are very tough. And so here's the same data I showed you before, but the blue is the added solubilization when you run the fermenter and mill at the same time. Now, milling has been known for a long time to be energy intensive as a pretreatment, But since the bugs can survive it and can do a lot of solubilization on their own, you let biology, ironically, at the substrate first, and then you bring in the mechanical treatment, and you have a much more easily milled feedstock. So the reigning paradigm is on the left. The alternative paradigm I want to tell you about, and am telling you about, we call it CCCB. We've been talking about consolidated bioprocessing, CBP, for a long time. Well, now that we add co-treatment, we don't want to have too many letters in our acronym, so we haven't been able to do any better than CCBP, but it's fundamentally different. It has different chances to succeed and, frankly, different chances to fail. But importantly, it completely avoids the two factors that are responsible for the current paradigm being so expensive. Completely avoids them, doesn't have them at all. No thermochemical pretreatment, no added cellulase of any kind. And so it also entails new challenges. So I've been talking to you about the front end, getting lignocellulose to the point that it's soluble. But let's now at least acknowledge a whole set of issues on the back end, because you've got to take something that you make soluble and convert it to a fuel. And if we're going to exploit the distinctive front-end advantages of thermophiles, we need to address the fact that, you know, a decade ago there were barely any genetic tools for these microorganisms, and they're not proven industrial microorganisms. So there's a whole bunch of intellectual challenges and applied challenges to actually making an applied, industrially robust microorganism, starting with, as I like to say, bugs from the mud. So there's been an extensive effort at Dartmouth with collaborators from the Bioenergy Science Center and the Center for Bioenergy Innovation and other people around the world to develop tools for thermophilic saccharolytic bacteria. This actually began in my lab in some ways an embarrassingly long time ago in the early 90s. The technology has been licensed to Enshi Corporation, who's looking to commercialize. And if you'd like to talk about that, I'd love to talk to you. But let's just realize that to completely utilize all biomass carbohydrate, it's necessary to engineer hemicellulose fermenting microbes that are compatible with the cellulose fermenting C. thermocellum. It's kind of curious that nature seems to divide these functions of hemicellulose fermentation and cellulose fermentation. You might think one bug could do all of them well. It's actually, there are almost no examples for which that's true. And so an early success was this Thermoanorobacterium saccharolyticum, and if I say that too many times, my time will be up. And we are able to engineer it to produce ethanol at essentially theoretical yields and commercially viable titers. We're not so far with C. thermocellum, but we've made a lot of progress towards this feasibility region from an economic point of view, starting with the little dots on the left. Well, what about techno-economic analysis? And so first I'm going to give you a high beam perspective. Let's kind of assume that it really works. I mean, and let's acknowledge this is speculative, right? We are not ready to build a plant. There's added development to do. I want to make that very clear. But we wrote and as I thought about how to do this back when, I said, well, it's logical to compare to an NREL base case, but I don't want to do that without them, because then they'll say we didn't get it right. So I called them up. I got lots of friends there. I said, let's write a paper together. So they specified the base case with dilute acid, enzyme produced at site, yeast, et cetera. And we first of all looked at some ways we could change the configuration. For example, producing fuel pellets as a co-product rather than electricity, which makes the system much less, you can do it much smaller. Then we looked at the R&D advances, and then we looked at an advanced scenario with all of them. And my favorite figure of economic merit, you can get into discounted cash flows and all the rest of it, but you can actually hide a lot of things in discounted cash flows. My favorite figure of economic merit is to take the capital cost divided by the net revenue, right? Payback period, really simple. Look at these results. So here is the base case technology with payback time in terms of years. This is NREL's characterizing their own technology, and this is actually at $2 a gallon ethanol. Ethanol's now less than $1.50, may not stay there, but the point is, this is a long way from being economically attractive, and it has to be huge. But as you layer these in, look at this bottom curve. You're talking about very short payback periods, and it's largely flat as a function of scale. So if you take nothing else from this talk, there are really, really different ways to approach this problem, and we've kind of been looking at it in terms of just one way. So we also took a lower beam perspective. I won't go through all the parameters, but sort of less aggressive, less ultimate, and I was actually surprised. So here we look as a function of the ethanol titer all the way down to 20 grams per liter, which is really low. And keep in mind, this is a discontinuous scale, so the base case at this scale is 25-year payback. And it's not very sensitive to the yield. We've already achieved these yields, and even at dilute concentration. So we're very, very excited about this as an alternative way to skin the cat. Well, I've been talking to you about ethanol, and there may be a reaction, there is in many audiences, some news. We don't need ethanol, that's old news, wasn't that done? Well, again, ethanol will be the lowest cost biologically derived liquid fuel forever, for fundamental reasons I could discuss with you. It has the potential to be cost competitive with fossil fuels on a BTU basis, but innovation is required to achieve that. I just demonstrated that. It is the logical proving ground for new technology aimed at the recalcitrance barrier, including but not limited to CBP. Cellulosic ethanol was abandoned too soon by United States funding agencies. Many solicitations over the last 5 years exclude ethanol, the DOE, the USDA, the NSF. It's a very high performance fuel in spark-ignited engines. It's actually used, 98% of the fuel in Indy cars is ethanol, right? So they chose that because it was about the best liquid fuel they could find in terms of performance. But the clear need for biofuels in order to achieve climate stabilization is for heavy-duty transport, not light-duty vehicles. The world is not looking to biofuels to decarbonize light-duty vehicles. Very, very clearly, I don't need to present the evidence. The world is looking to batteries to decarbonize light-duty vehicles. But there is increasing recognition, and I'm pleased that we'll be having an entire presentation on this, so I'm just going to say a little bit about it. Increasing recognition of the potential of lignocellulose going to hydrocarbon fuels via ethanol. Essentially, ethanol is the lowest priced intermediate that biology can make. And then let industrial chemical catalysis take over. There's an excellent review from Nature Reviews in April on the chemistries of this. Lanzatech is pursuing this. Vertimas, which John Hannon is a representative of, is pursuing it. Here is a remarkable analysis that Vertimas has done. Starting with cellulosic biomass, if you're going to make ethanol, somewhere in the process you have wet ethanol vapor as an intermediate. You've already made the ethanol, you're halfway through recovery. And you can look at the cost of continuing that to anhydrous ethanol, or alternatively to making hydrocarbon fuels from the same intermediate. And through a recent development effort, Vertimas is now here. They project it will be here. In other words, they project they can make hydrocarbon fuels from ethanol that are no more expensive than ethanol. If that's true, that is an absolute, you'll hear about it from John, it's not my data, it's his, but if that's true, it's an absolute game changer. You see a lot of research, I won't mention the institutions, but we all know them about making jet fuels, for example, with yeast. They're going to make like C16 molecules. That will never be as cheap, ever. That will never be as cheap. And one simple reason is the more a product looks like a membrane, the less happy a cell is in the presence of that product. And a C16 fuel looks an awful lot like a membrane, okay? So, but it's also true, as exciting as this is, for the purpose of cellulosic biofuels, it's only as good as making inexpensive cellulosic ethanol. So in my opinion, making cellulosic ethanol is both a commercially and technically justifiable next step, but it's also enabling for one of the most promising pathways to actually get to the hydrocarbon fuels. Well, let's talk about people. And so this is the way the UN represents their Millennium Goals. And I would argue that energy from biomass, I just spent 2 weeks in Africa for the UN Environment Program in Malawi and Kenya and Uganda evaluating a bioenergy project. Energy from biomass can positively impact most of the Millennium Goals, which is a remarkable statement and is not one you could make about most of the other renewable energy sources. So data from Brazil. There's 500,000 people who work in sugarcane and ethanol, which is the highest in the ag sector. They have the highest participation in the formal economy. In other words, I don't know how much time you've spent in developing countries, but it's common to have people lining up and trucks drive up and they just take people from the day and they say, we're going to pay you when you're done. If they get sick or anything, they're not part of the formal economy. Higher wages, education, and mobility for these workers compared to the average for agriculture, and demonstrably higher for the children of workers in these industries than their parents. Okay? And so the tax revenues go up, more investment in education and social services if you compare communities that have these plants to communities that don't. Let's talk about, that's data of what's already happened, retrospective. Let's talk about a prospective example. Mozambique is one of the 10 poorest countries in the world, and yet it's really rich in both land and fossil resources. And so Marcelo Moreira et al. Has developed detailed land maps of land use, climate, soils, habitation. They estimate that 21 million hectares in Mozambique has medium to high suitability for sugarcane. This is a Brazilian group that knows more than a little about sugarcane, and ethanol for that matter. After applying every filter they could think of, I'm not saying you couldn't come up with different conclusions. Let's take half of that, for example. 10 million hectares of sugarcane bioenergy. Well, if you did that, and you just go through the numbers, you would produce 76% of the, it's not going to happen anytime soon, but to give you a sense of how big it is, 76% of the transport fuel and 44% of the electrical generating capacity of the 44 sub-Saharan African countries other than South Africa, and $46 billion of revenue, which would be compared to the Mozambique gross domestic product, which is $15 billion. So, I mean, the problem is not that this can't be big. And so we did a really interesting exercise. We said, let's say you take 12 points, and by the way, this is the paper that I proposed to submit to Applied Energy, is on this last piece. Let's say you take $12.7 billion of US investment over 25 years, and you look at sugarcane bioenergy, which is not happening in Mozambique, and you look at oil and gas offshore, which is happening big time off of Mozambique. Well, it turns out you get about 4-fold lower greenhouse gas emissions with the sugarcane, and you would actually get very close to zero, by the way, if the full supply chain was decarbonized. But this is taking it as it is when that's not true. In other words, distributing the fuel, the agriculture, all the rest of it. And we need to have a decarbonized agricultural sector. You actually get more for the same dollar investment. You get more energy yield out of the bioenergy. And then look at this. You get 8-fold greater tax income for the government. 8-fold greater tax income for the government. This is based on input-output analysis to look at direct and indirect effects across the economy. 4.5-fold greater GDP contribution, and 36-fold greater job creation. So this is another interesting study we've submitted. Andrew Ali led this one. So what does food, the wrap is, yes, but aren't we going to compromise food security? And there's a real basis of concern. I don't mean to be poo-pooing it. But let's ask ourselves what food security depends on. So here we have data from over 100 countries, the Global Food Security Index. And so here it is as a function of land quality, actually a negative correlation. The higher the land quality, the global food security does not increase when you have greater land quality. It's all over the map. If you look at the amount of land available at a national level, basically most of the people have not that much land per hectare, per capita, with a few exceptions. But again, there's some very secure countries with not much land and some very food insecure. The pink is Africa. They generally cluster towards the bottom. What about agricultural intensity as measured by fertilizer? Again, some of the most food secure places use very little fertilizer, some of the most, very little fertilizer, and then some of the most food insecure places also do. Well, what about just, do you grow a lot of stuff? Here's cereal production per hectare, again, all over the map. However, if you look at personal income, you get a bloody good correlation. That's actually better than the correlation you often see between personal income and energy use, all right? And if you actually go through the multivariable analysis, so here we have a 1, 2, 3, 4, 5, 6, 7, 8 variable model, gives us an R squared of 0.948. If you only look at household income, you get virtually the same R squared. And this actually is also backed up by an excellent empirical study where they did household surveys. And again, they found that household income is the thing. So food insecurity and poverty are actually more one problem than two, all right? And so the best thing you can do if you want to make people more food secure is to give them a job. So energy from biomass can positively impact most of the Millennium Goals by creating value in poor rural communities. So in the project that I was working on in Africa, we looked at the impact of bringing electricity, and I think there's been this idea that if you bring electricity to African countries, you will change everything. But what people are finding is if you don't bring a means to generate economic value, it's not that bringing electricity isn't useful. Of course it's useful. But if you don't bring a means for economic value generation, not much happens. So this is a critical step towards upliftment. Bioenergy appears to be distinctively well-suited among a limited set of options. Interesting number, the total philanthropic aid entering the African continent, depending on the price of oil, is very similar to the amount of money leaving the continent to bring oil in. So you basically wiped out all of that effort by your energy picture. I'll let you read these. They summarize what I said. I've gone a little bit over time. I don't tire of this subject easily, but I've used most of my time. We could take however many questions Scott thinks is appropriate, and thank you very much.
Okay, thank you so much. That was such a thought-provoking talk. We have to have time for some questions, so please. Yes, please.
A common complaint about cellulosic ethanol as a fuel is its incompatibility with the distribution infrastructure. Is there a way around that?
Yeah, I mean, you know, if we were convinced it was a good idea, this would be a snooze to solve. In Brazil, the minimum amount of ethanol is 25%. When you buy gasoline, it's at least 25% ethanol. I wrote a paper with Roberta Nichols from Ford a long time ago. In 1991, she said this problem was solved. There are costs to moving ethanol around and ethanol blends around, and so, you know, the question is who's going to bear the cost. But right now, I think the feeling is, with very little optimism, this is worth doing. Why bother? But technically, it's a snooze.
Thank you.
And again, we may be able to use ethanol to make other fuels that are, you know, as I mentioned, for the heavy-duty applications.
Yes, please.
Great talk. It's refreshing to see a new take on cellulosic ethanol. But I've been in this area for a while, and I was even at RPE last summer doing an internship. And even just mentioning the word ethanol in the energy realm put the bad taste in people's mouths still. So I think this is really exciting, but what's it going to take to get the public and the government, you know, more involved again and willing to put millions of dollars?
First of all, it may not happen first in the US. I'm more optimistic about it happening in Brazil for various reasons, and that's where I intend to try to push to make this happen. But secondly, actually, because of exactly the experience you describe, and I can't describe it any better, I agree 1,000%. One of the people working with me made a little alert anytime the ARPA-E website changes. Turns out a guy named David Babson is now an ARPA-E program director, and he thinks ethanol is wonderful as an intermediate. So there are new opportunities, and yeah.
Yes. Yes, please.
What kind of conversion processes are you thinking of from ethanol to other products?
I'm going to let the guy behind you who's got a whole talk on that stay around for John's presentation. And I think I should stop.
Okay, well, let's thank Professor Lynd one more time.